Good evening, everyone. I'm Irene Pease, your friendly neighborhood astronomer, coming to you from Brooklyn, New York. But it's a great, big, friendly neighborhood, friendly universe out there. So, wherever you're tuning in from, hope you have some skies. Tonight, we're going to be looking at black holes because who doesn't like black holes? We're going to be just kind of taking a little stroll through our neighborhood, and by neighborhood, I mean the universe, starting kind of local, saying what's up in our friendly neighborhood skies, and then kind of moving out from there. So to start off, we have some visuals. If you like the visuals that you see, you can download them for free. Right now in the background is OpenSpace, which you can download for free at openspaceproject.com. It's open source software you can use to fly around the universe in 3 dimensions, and you can even load in whatever data you want. Which, have to say, I'm kind of proud of myself. I actually loaded in a map tonight that you will see later. Also, I'm going to be clicking over in just a moment to Stellarium, which you can find at stellarium.org, and I really like using that for kind of planning my observing and what's going to be up in the sky and figuring out when the moons are going to be where and whatnot. So, some fun software. So let's go ahead and just click over before we get to the black holes and all their glory. We'll see what's up in the sky. So this is it for now in Brooklyn. Again, this is the background, the landscape that we see here isn't actually Brooklyn. It's Garching in Germany, kind of in honor of the excitement we had. Some kind of exciting things uh, in their missions in the last week or so. But yeah, I wanted to take a look and see tonight we have the moon very close to Jupiter and Saturn. So if you're wondering what those bright things are near the moon, that's your answer. Jupiter and Saturn. Jupiter's the brighter of the two, very bright. It's one of the brightest objects in the night sky after the moon and Venus. And tonight it's actually less bright than Mars because Mars is so bright. So if you look over towards the east, the really bright thing over there that looks kind of reddish or orangish, that's Mars. And in case you're having trouble picking out the bright orange thing over in the east, in another couple nights, the moon will be over there too. And actually, a fun thing to look for could be actually trying to find the moon just after sunset. So, or actually just before sunset. If you're able to see the moon before the sun sets, or the the Mars before the sun sets, that's kind of a fun challenge. Since Mars is currently so bright because we were just near close approach. A few weeks ago, Mars is going to be fading, so it's not going to be this bright forever. That's a lot of numbers. But it does tell you how bright it is. Another great thing that Stellarium does. If you want to know how bright Mars is going to be compared to other things, Stellarium can tell you that. So tonight, moon is near Jupiter and Saturn, and later in the week, early next week, the moon will be near Mars. So that'll be a really cool view. And Uranus is labeled over here. You won't really be able to see that very easily. I wouldn't recommend trying to find it just yet, not with the moon so close, but that is something that I want us to be kind of working towards. So a fun thing to try to do is to see Uranus with the unaided eye, not during the day, but at nighttime. So last week, we looked at a couple constellations that we could use as markers to try to get to know our way around that relatively blank looking part of the sky. So if anyone was able to find the square of Pegasus, that big square shape of relatively bright stars, and then just due south of it, the little circlet of Pisces, then you get all kinds of bonus points. So again, later in a few days or so, next week, we'll see that Mars and the moon are kind of near this kind of neck and the other neck of the fishes. So again, some imagination required there. Stellarium helps you with your imagination if you need it. Yeah, Pisces is supposed to be a couple fish tied together with rope. Not seeing it, but there you go. So it's going to be harder to see with the moon right there. So maybe try that in the next few days before the moon gets so close. But your challenge for this week is to try to find any more of Pisces and find Aries, right? So if you found the circlet or the little ringlet here, you can try to follow this trail of stars down to this southern star here and then back up. This one over here, Eta Pisces, is a little bit brighter than some of the others. But if you can find this kind of V-ish shape of very, very faint stars, then you get bonus points. And finally, if you can find over past the V, there's this little hook. The star, it's kind of out there, but really it's these two stars. That's the kind of little hook of Aries, the ram. So that's, yeah, supposed to be a goat. I don't know. But if you can find the V of Pisces, then you should be able to see these stars as well. So that's kind of a super fun challenge for the next week or so. Obviously, look at the planets because they're amazing. They're all pretty amazing out there right now. Mars in particular, still very close enough to see some of the dark markings on it. But when the moon is not over in this part of the sky, also look for some of these fainter constellations if you have a dark sky that you can view from safely. Safety first, kids. So that's kind of your night sky, and not really any black holes that we can see in the night sky per se. Not that we can really see black holes, but I wanted to talk about where some might be and how we can try to detect them. And by we, I mean other people who do this full time as scientists. So we'll jump over to open space again. And again, this is basically all real data in here. So this is kind of almost what you would see if you were out in space orbiting around the Earth very, very quickly. You'd have to move really quickly to see it go this fast. But I wanted to go ahead and take a look. If we move out, where are some black holes? Well, all over, but not very close is the short answer. So if we just kind of look around our night sky, the main thing we see is the Milky Way. That's where most of the material in our galaxy is. So we see that as kind of a streak across the sky. And we do see kind of the central part of our galaxy in the summertime in the northern hemisphere. And that's over kind of by where the planets are, where Jupiter and Saturn are in our night sky this week. But there's actually a really big black hole over here that we'll get to in a little bit. But just kind of all along the galaxy is where we're more likely to find black holes. So 3 different types of black holes, really 2 that I want to just touch on tonight. The first one, the micro black holes, probably they've all evaporated away, so we're not really going to talk about them, but I just mentioned them, the end. The next type of black hole I want to talk about and point out where some of them might actually be are the kind of stellar mass black holes. So the ones that have the mass of like a star, or 10 stars, or 100 stars, but aren't like super massive, like billions of stars. That's a lot. So we're going to start off with, just a few stellar mass things. So where would those be? And how in the world do they form, and how do we detect them? Well, one way that we think they form is from really massive stars that basically use up all of their nuclear fuel and end their life cycles. And they give off a lot of energy and a lot of material, and they basically explode. We're just going to call it an explosion. And we have some blobs here. They're not actually shaped like that. So these are representations of a data set of supernova remnants. So those are kind of what they sound like, because astronomers aren't really that creative when it comes to naming things. We're pretty straightforward about stuff. So supernova remnants are the remnants, the leftovers from supernovas. So again, supernovas are those really big explosions from really big stars. Stars much, much more massive than our sun. Our sun is not going to go supernova. It'd have to be quite a bit larger, at least 10 times the mass, in order to go supernova at the end of its life cycle. But all these blobs are from stars that did go supernova. And when a star goes supernova, the core of the star can get very, very compressed into something very, very dense that could potentially, in some cases, possibly collapse into a black hole. So at the centers of these big blobs, they're actually representing huge clouds of gas expanding out into space. the sizes of these aren't necessarily representative of the extent of the gas that's been expanding out that was kind of burst off from the supernova. But it's more indicating like how close they are to us. So the bigger ones are closer to us. But you notice they are mostly along the plane of the galaxy. If we kind of take a look up above the galaxy, not that there's really up in space, but yeah, we consider that kind of side up or north. And if we look down below the plane of the galaxy, yeah, pretty blank. So they're mostly all in the plane of the galaxy because, again, that's where most of the stuff is. So that's where we're going to find these wonderful objects. So at the centers of many of these could be black holes. Probably not all of them. A lot of what happens to the supernova remnants is they have pulsars or neutron stars at the centers of them. Those squares are really big. Let me make them a little bit smaller. So that data set, the squares, not I think those are hexagons, septagons. The squares though are sort of down, more manageable size. Those are the pulsars. Again, the pulsars are actually going to be round. Real stars are round. They don't have those zigzaggy, pentagon-y shapes. But those are where pulsars are. And so this is a data set representing the locations of pulsars in our galaxy. So if a star doesn't collapse into a black hole, if the supernova, when a star goes supernova, it doesn't collapse into a black hole, probably what's left behind is a pulsar. So you can think of all these pulsars, these very, very dense stars, as failed black holes. They failed to become a black hole, so they're not as cool. They're still pretty neat, but they're not black holes, so, you know. But yeah, so pulsars are very, very dense, and we call them pulsars because they pulse. So they have these very strong magnetic fields and give off jets of radiation from their magnetic poles. And as they spin, those jets of radiation pulse towards and away and towards and away and towards and away from us, sometimes very, very fast. So if you can imagine something like that, like this big pulsing, very charged and magnetic, dense star, getting just a little bit denser, that's basically what becomes a black hole. So not black holes. So let's just go ahead and turn those off for now. But they give off this radiation, and black holes are going to do something similar. So black holes give off very energetic electromagnetic radiation. So light at the really energetic, high energy end of the spectrum, like gamma rays, X-rays, lots and lots of X-rays, and they give off a lot of low energy light, like the radio part of the spectrum, not necessarily gumming any light coming out of the black hole because black holes are pulling everything in, but they have these disks of material around them, kind of whirling and swirling because of gravity, and I'm gonna kind of try to model that a little bit with our solar system. They have this whole disk of material around them that's spiraling in, and as the material spirals in and is falling in towards the black hole, it gets very, very hot. And that material that's in what we call the accretion disk, that's what's giving off all kinds of energy, all kinds of radiation. So that's the part of the black hole that is a lot easier to detect than the black hole itself, that central region of space that light can't escape from. So if you kind of look at our solar system, it's kind of similar concept of like a disk, right? So if the sun formed, that's the sun way in there, and then we have the planets' orbits shown, so the inner planets in there, and then the outer planets. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus. The outer planets are really out there. So when the sun first formed, there was all this material swirling around it like in a big disk that eventually formed the planets. And actually, this is kind of the scale of some of the more massive black holes, some of the supermassive black holes. Not stellar mass that would have come from a supernova, but some of the supermassive ones, like the one in the center of our galaxy, that would have a black hole in the center, and then an accretion disk of all this material, like the size of our solar system. So that's a lot of stuff falling into a black hole, getting all hot, energized, and whatnot. So I did want to show this map that I just have to say I'm super proud of it. Because this is one of the cool things about open space is if there's not a map or an object or something that's in there in the data set that comes with it, you can find one and put it in yourself, which is what I did today. So I got this really great X-ray map. Whoa! Okay, there's like the one data artifact that we're looking at there. um, so this is an AllSky survey in the X-ray part of the spectrum. And I didn't get it synced exactly. It's almost, so like you can tell like this blob should correspond with this blob, so it's a little bit off. But that's my fault. But it's mostly synced up, so we should be able to see kind of along the plane of the galaxy here. And I'll go ahead and turn off our Supernova Remnants. And this is actually a relatively new map, so I was pretty excited to find it. This is from the Rosita mission. It's a Russian-German mission. They launched this satellite out into space at the L2 point, so it's out far beyond the Earth, kind of in a line from the sun to the Earth, and then out beyond the Earth, what we call the L2 point or the Lagrange 2 point. And so it's out there pointing away from the sun, just kind of like doing this full survey of the sky in the X-ray part of the spectrum. And so this is the data that they released just this last summer. So it launched only last year in 2019, and it's out there. We got this data, their first release on June 2020. So looking forward to more of what they're going to be releasing. Very cool data set. So you can see some of these bright blobs. Actually, some of these, I don't think it's that bright one unless I'm turned upside down, is actually one of the, probably actually a black hole. So either that blob, there might be another blob over here. Nope, I'm going to go with that blob. Cygnus X1 is a very bright X-ray source in the constellation Cygnus, which is a northern constellation. And that object is thought to be a black hole, so a stellar mass black hole. So we're seeing more than just black holes here. So some of the blobs might be from the accretion disks around black holes. Some of the blobs that we might see off the ecliptic are actually some galaxy clusters. So some of the nearby groups of galaxies actually show up here as little white spots. I'm pretty sure that one, I want to say that one is the Virgo cluster, because I know the Virgo cluster definitely shows up in this map. So some really cool things. So we can see some of the spots in our galaxy, and then we're even seeing collections of other galaxies, which is pretty exciting. So if I try to look back towards the center of our galaxy, I had mentioned that we had a supermassive black hole in the center of our galaxy. And in order to find it, I might have to kind of dim the X-ray. But I want to leave it up there because I'm just so darn proud that it's there. So we'll fade out the X-ray a little bit and so I can see where we are in our galaxy. So if we look back towards our galactic center, I think that was back over here. We have this way. A supermassive black hole that was actually in the news relatively recently for people who follow like Nobel Prize stuff, you know, just that. This was actually one of my favorite videos on the internet. there's a lot of stuff on the internet, but one of my very favorite things my top two things, really, both of them are kind of astronomy related. But one of my very favorite things actually is related to this supermassive black hole in the center of our galaxy. So if we look in towards the center, I'm just going to bring up some constellation lines as markers to help orient. Um, so right around in here. So there's a lot of dust and stuff in the way. So even on this awesome X-ray map, it doesn't quite show up because I'm pretty sure that point is actually oriented. But right around in here is actually where the dead center of the galaxy is. And we do have a supermassive black hole in our galaxy there. So it's called Sagittarius A star. So if you want to, make like your, super good friends with it, Sag A star. And I think there's the one. This video, I call it a video, but I mean, really it's years and years of data. It's almost like 20 years worth of data that was collected by the Keck UCLA Galactic Center group. So all these images and animations were created by Professor Andrea Ghez and her research team at UCLA and are from data sets obtained with WM Keck telescopes. And you might recognize the name of Professor Andrea Ghez because she just was a co-winner of the Nobel Prize, no biggie. So, so I just wanted to play through this real quick because this is actually showing another way that we can detect black holes, especially these supermassive black holes. So in addition to just trying to look for the signals, like the light, being emitted by material in the accretion disk, what this group did was they actually watched stars. So all those spots that you're seeing are stars orbiting around the central, that thing, the center of our galaxy. So basically, by using the laws of gravity, what we know about gravitation, and seeing how long it takes these other things to orbit around, you can basically measure the gravitational pull, and you can figure out that the thing that's in there has to be so dense that it has to be a black hole, and you can find its mass, and it's just kind of amazing that it's like, we're using gravity because, well, gravity is one of my favorite forces. It is my favorite force. So we're just going to say that one more time. So I'm going to put a link to this video so you can watch it ad nauseum, as you should, because it's just utterly amazing. So again, it's just, was it like 15 years worth of data that they watched and plotted the positions of all of these stars to figure out how they were moving. And then they were able to use that to help calculate the mass of that black hole. And that just kind of blows my mind. So another way that some people have tried to look for black holes, if we pop back over to open space, I think I had the other image in here, was using gravitational lensing. So also using gravity, but that hasn't been like such a huge thing. It's so it's such a chance encounter. Like a lot of times, if you look at the stars in the sky at night, most of them are, or the majority, I'll say, that we're seeing are 2 or 3 or more stars. So our sun is kind of like, an oddball, being just a single star. It's not the end of the world, but it's it's cool to be single. But a lot of the other stars have pairs, and so you can do something kind of like what the Keck group did, and watch the companion orbit an apparently empty spot and figure out like, oh, that must be a black hole. This is just an image of gravitational lensing, not from a black hole, but just from a really massive galaxy. So usually we think of this as a detector for, big blobs of dark matter. And in theory, and I think they have actually successfully used this to find some black holes, but again, it's more of like a chance encounter. So, nah. Gravitational lensing is great, but it's not going to be your favorite thing for detecting black holes. So, so we have our just looking out in the sky and seeing this high energy. We have a little bit of lensing. And then I just wanted to show where a lot more of these black holes are. Actually wanted to turn on another data set, which I almost never turn on from inside the galaxy. So we will leave the galaxy because I haven't really gone out much beyond the solar system lately, exploring. But I do want to turn on this other data set. It's the Tully set of galaxies. So a collection of lots of galaxies. There they are. And a bunch of them are labeled. Yeah, that's great. Okay. We don't need those for now. So yeah, so all of these galaxies. So most of these galaxies, these are all pretty massive galaxies, some bigger than others. But most of them are going to have massive black holes in their centers. So even if we look up towards, I can find, I almost feel lost here, up towards Virgo. And I think in the past, and someday again, we'll be exploring that Virgo cluster. So this is our local group, or the direction of our local group. So one of the galaxies in there, M57, has a super duper massive black hole. Like, we have a massive black hole in the center of our galaxy, Sagittarius Star, but M87's black hole just kind of blows it away. It's kind of like, oh yeah, pretty cool. Just not as big as that one, but it's pretty big. So if I just fly out, we call this flying, fly out of our solar system, and kind of out of our galaxy. There's the constellation lines. That's our corner of the galaxy. And now my data set's getting grumpy with me because it's too much data. There goes the Milky Way. All right, so we're out here amongst the galaxies. So all of these pretty much have black holes, supermassive black holes at the centers. Most of the large ones do. And it gets even better. So if we move out even further, beyond the galaxies, so if we're looking further and further away, this is about, right around here is about 1 billion. Yeah, about 1 billion light years away. And we start to see these other dots. So far these are all galaxies, but get some red dots on. Yeah, those red dots. Okay, the red dots, mostly beyond the galaxies, those are quasars. So those are very distant, and so very, I guess you could think of them as old, but really they're from the young universe. So we're looking back in time. So they're very far away. They're from the very early universe. And those we think are powered by super duper massive black holes with like super duper massive accretion disks in their galaxies. Those things are so bright, they're completely outshining the rest of their galaxy. So again, we have a really great supermassive black hole, Sagittarius Star. And I think it suits us. Like, it's calm and it doesn't completely outshine the rest of the night sky because, there's other cool stuff to see in the night sky. So it's nice to be able to see all that. But these ancient relics from the early universe are much, much brighter. So basically all these red dots, billions of light years away, are more super duper massive black holes, we think, powered by all kinds of infalling matter, super huge, very energetic accretion disks. So that's where you can find some more black holes. So we have some black holes in our galaxy. We can see those a little bit by like gravitational tugs, where they tug on nearby stars, or when their accretion disks give off really energetic light, or sometimes just radio light. And then the rest of the really cool black holes are in the centers of large galaxies. So most galaxies have a supermassive black hole in their center, and those we can detect, some again by gravitational effects, but also by looking and seeing the light that's given off by their accretion disks. So that's my short story, a little stroll out towards the edge of the universe, not to the edge. We'll get to the edge another day, right up against the fence of our neighborhood, so to speak. But we'll come back a little bit more local so I can leave you a little closer in here. And yeah, there we go. Kind of coming back to home sweet home. We'll just stay out here outside of our galaxy. So again, whoops. when I say your friendly neighborhood astronomer, I'm being pretty loose with the word neighborhood. So this is our galactic neighborhood that we took a little tour around tonight. But again, if you like the visuals, definitely check them out. You can find Stellarium at stellarium.org. You can find Open Space at openspaceproject.com. You can find more about Friendly Neighborhood Astronomer at friendlyneighborhoodastronomer.com. I'm Irene Pease, your friendly neighborhood astronomer. Thanks for joining me for this little stroll around our neighborhood. And I'm just going to wish you clear skies and be safe out there.